This is Mr. Boyce, and we are going to go over Unit 11 and 12 exam. So whether you are watching this to prepare for a retake or just trying to catch up ahead of finals, I do welcome you. And so we're going to go ahead and go through this. Okay, first thing we're going to do is we're going to go through what is called a heating curve. And so real quickly, the way a heating curve works is you have, in this case, it's water, and below zero, this is ice. Between 0 and 100, this is going to be water. And then from 100 to however hot it gets, that's going to be steam. And so what we want to do is we want to look at this question. We want to see just how far do we need to go? Like which parts on this curve do we actually need to track? The most you can go is from sub-zero all the way to above 100, from ice to water all the way to steam. But you don't necessarily always have to do that. So in this case, our question is saying we have 72.3 grams of ice at 15 degrees Celsius. So if we're at 15 degrees, that means we're already water. We don't need to worry about this whole ice area here. This is already taken care of. We've already completed the phase change from ice to water. So we are at 15 degrees. We are right about here. Okay. And heat energy is added until it becomes steam at 145. So 145, that is after the phase change to steam. This is going to be somewhere over a little bit off the charts here for this temperature. So we need to think, okay, what is it that we need to worry about? Well, we need to go from 15 degrees to 100 degrees. Once we get to 100 degrees, then we need to go through a phase change. So if you think about it this way, if you put a pot of water on the stove, at some point it's going to start boiling, but it doesn't just all instantly turn into steam. It takes a lot of energy to do that, but the water will not go above 100 degrees. Well, obviously the water at home has some impurities, so it'll vary a little bit, but for the most part, the temperature will stay the same. And so all the energy it's going to take to convert all of that water into steam, that's a lot of energy. So we're still adding energy, but the temperature is not changing. So this is called a phase change right here, a phase change. And so we have to account for the energy to get there. Now, once we finish the phase change, we're still at 100 degrees Celsius, but now we are in the steam mode. And so now we can go from 100 degrees to 145. So we're going to want to know how much energy that's going to take as well. So we have 3 calculations and we're done. So let's start with number 1. And that's going to be going from 15 degrees to 100 degrees. And with that, that's going to be a change in temperature. In other words, a delta T. And so I'm going to use Q equals MC delta T. So Q equals MC delta T. And this is for water. So I'm going to put my mass of 72.3 grams. Okay, remember, if for some reason this is not in grams, you would need to convert it to grams. C, now we have different C's, C values, depending on what it is. So you have ice, water, and steam. Whoops, disappeared. So we have a value of C for ice, water, and steam. Now water, you do need to know the C of water, and that is 4.18 joules. And that also happens to be 4.18 joules is equal to 1 chemistry calorie. So if the question is in calories, you can use 1, but we generally, our questions in this class haven't been in calories. Okay, and then delta T. And remember, delta doesn't just mean change, it always means final minus initial. And so for this change, we were trying to get to 100, and our initial is 15. So 100 minus 15 is 85. Okay, and very important, pay attention that C is in joules. And the answer we want is also in joules. So this is going to be good. We can just kind of keep the answer the way it is. And so in a calculator, I'm going to do 72.3 times 4.18 times 85. And that's going to come out to 25,688.19 joules. So this gets us from 15 degrees to 100 degrees. Now, next is the phase change. That takes a lot of energy. If you think about it, how much energy would it take to boil off an entire pot of water? Probably a bit, probably a lot. So let's just go ahead and move on to number 2 for the phase change. And for the phase change, I've got a delta H of fusion and a delta H of vaporization. Well, we are vaporizing. We're going from liquid to gas. So we're going to use the delta H of vaporization. Now, you can use this as a conversion factor. Kilojoules per mole. That means for every 1 mole of water, I'm going to need 40.7 kilojoules of energy. Now, I don't have 1 mole of water. I have 72.3 grams of water. But we're pretty good at this point in converting grams to moles. So let's start there. So 72.3 grams of H2O. So I have it in grams, but I don't want it in grams. I want it in moles, and I can do that. So units always move down to moles of H2O. So we know that 1 oxygen and 2 hydrogens is going to equal right about 18 grams. Okay, so now I have it in moles, but I don't want it in moles. I'm going to move on from there. So I'm going to take my unit and bring it down. Moles of H2O. And here's where I can use my conversion factor, moles to kilojoules. Okay, and according to our delta H of vaporization, 1 mole of H2O requires 40.7 kilojoules of energy for this phase change. Now I'm going to go ahead and do one final conversion here, and that is because I want my answer in joules. So I'm going to take kilojoules. Again, I'm bringing my unit down, and I'm going to convert that to joules. And 1 kilojoule is equal to 1,000 joules. K is 1,000. So put that into my calculator, and that is going to give me a nice giant number of 163,478.3. And I get that by doing 72.3 divided by 18 times 40.7 and times 1,000. And that's going to give me 163,478.3. Double check that. And it's actually 0.33333. So let's just put 33. Okay, and that is in joules. This is what I want it to be in. Okay, and then finally, we're going to do one more. And this is Q equals MC delta T, because at this point, I've gone from 15 to 100. I went from 100 water to 100 steam. We did our phase change. And now we need to get from 100 to 145. So Q is the same, 72.3. C changes. The C of steam is 2.02 joules over grams Celsius. So let's put that in there. Whoops, I started to write joules. So that is going to be steam. So 2.02 and delta T, final minus initial, 145 minus 100 is 45. That's how many degrees we changed. Okay, and the answer to that is going to be 72.3 times 2.02 times 45 is 6,572.07 joules. And that gets us from 100 to 145. Lastly, what I'm going to do is just add up these three numbers because that's the total amount of energy that, oops. I'm going to add up these three numbers because that is the total amount of energy that we needed. And if I add up those three numbers, that is going to come to 195,738.59 joules. Now, one thing is, when it comes to significant figures, notice that all of our numbers in the problem have three significant figures. So a perfectly valid, in fact, preferable answer would be to convert this to scientific notation. So 1, 2, 3, 4, 5 times moving the decimal place. Wow, that's really not the best handwriting. And that's going to equal to 1.96. So three significant figures times 10 to the fifth power. So this answer, at least in 2025, I would accept, although if you're watching this any other time, I really should have been more focused on significant figures. So that would be the correct answer. Okay, so potential diagram. So this is just energy in, energy out is basically a way of looking at this. So let's say the delta H of the forward reaction. So let's put some numbers on here. Let's say, 0 to 100. And let's say that this point right here is, let's say 30. Okay, and then up here where it meets, let's just say that's 50. Not perfectly to scale, but it's fine. Now for the forward reaction, that means we're going to go from 50 on our start to 30 at the end. So our delta H is going to be, again, final minus initial, and our final would be 30, and our initial was 50. So for the forward, our final minus our initial is going to equal 30 minus 50, which is going to be negative 20. So that would be our delta H for the forward. Now delta H for reverse would be exactly the opposite. So in that case, we would be going this way, and that would make this our final, which is 50, and 30 as being our initial. So for the reverse reaction, we would do final minus initial again, but that would be 50 minus 30, and 50 minus, whoops, yeah, 50 minus 30 equals positive 20. So the reason I'm always saying final minus initial is in both cases, the answer is 20, but one of them is negative 20 and one of them is positive 20, which are very different from each other. So make sure you're keeping track of what your delta actually means in this case. Also, let's talk about endo versus exo. So for the forward reaction, I am losing energy or expelling energy, if you like. So this is going to be exothermic. And then for my reverse reaction going the other way, I am starting at 30 and ending up at 50, which means I'm gaining energy from the surroundings, and that is going to be endothermic. Be very careful. Questions will often ask you for forward and reverse reactions. Okay, here we go. You're going to see questions like this. This is delta G equals delta H minus T delta S. And whether the chart looks exactly like this or like something different, it's still basically the same thing. For me, I find the easiest way to do this is to write the reverse reaction out first. Now, this question happens to answer several questions for you to start with. So this question could have just started with the synthesis of SO2 and O2, although that one, unless you know what it is, that would be a little harder. But predicting, say, a double replacement reaction is something we do a lot. And that would be something that you would have to do if the question asks you to. Now, in this case, the question just goes ahead and gives you the reaction and even balances it for you. But again, you might have to do that yourself. But that's something we're all pretty good at this point. So what I'm going to do here is I want delta H and I want delta S because I need them for this formula right here. And so delta, again, final minus initial. So let's write this reaction as final minus initial. So instead of writing it as a reaction, I'm going to write it basically as a math problem. So I'm going to write this as, let's go ahead and put this in regs, 2 times SO3, and I'm going to start with, say, let's do delta H. And so here are my delta H values. Notice these are in kilojoules, which is good because delta G has supposed to be in kilojoules, so great. So delta H 2 times SO3, actually I'm not starting with delta H, I'm starting with just the general formula here. So 2 times SO3, that is my final, minus my initial. And that would be 2 times SO2 plus 1 times O2. No point in writing 1 times, so let's just put O2. And remember, this is the complete final minus the complete initial, so I'm going to put parentheses around all of it. Now, to get to delta H and delta S, it's a little bit easier if you took the time to write this because now you're just subbing in numbers for from the chart into the same formula you just wrote. So let's start with delta H. And here we go, right in between the red lines here. This is delta H. Okay, and let's go ahead and start. So 2 times, and SO3 is negative 396. That's right here, SO3 seems negative 396 minus, I've got 2 times SO2, and SO2 is negative 297. And then O2 is 0. So in this case, I can pretty much just ignore the O2, but I will caution you, when you are doing the math, don't always just ignore the zeros because there are situations, say you had you know, 0 minus a negative number that could switch the signs. But in this case, it's plus 0, so it's really not going to matter to us. Okay, so let's throw this on the calculator, and that's going to be parentheses 2 times negative 396, close parentheses, minus parentheses 2 times negative 297, and that is going to equal negative 198. And that is, of course, in kilojoules. Okay, and then for the next one, we're going to look at delta S. So let's just keep track. I'll use a different color here. Delta S. And again, I'm still looking at this same reaction, and I'm just plugging numbers into that reaction. So 2 times, and now I'm pulling from the delta S. And notice this is in joules, and that's a problem because I need it in kilojoules, so we'll deal with that later, but keep that in mind. So 2 times, in this case, SO3, which is 257, so SO3, 257. So we're just plug that number in, just plug and chug. Okay, minus, in parentheses, 2 times, again, I'm just following this top one, SO2, that's 248. Okay, plus And this time, there is a value for O2, so we want to put that in there this time, plus 205. I'm going to go ahead and put the parentheses around the entire thing because I want to make sure the calculator sees that I want the whole sum of the final minus the initial. So let's go ahead and put that into the calculator, and that is going to equal negative 187 joules. Now I need this in kilojoules, so I'm going to divide this by 1,000. And to divide by 1,000, you really just need to move the decimal place over 3. So this would be the decimal place 1, 2, 3. And so that is going to equal negative 0.187 kilojoules. So now I have my delta S, my delta H. I'm almost there. The last thing I need to worry about is temperature. And remember, in these problems, standard room temperature is considered 25 degrees Celsius. It does happen to say that in this question, but it won't always say that. You need to make sure you know that. That's different than SCP with gases. So chemistry can be weird sometimes. So 25 degrees Celsius. Now I need this in Kelvin because this is not a delta T. It's not a change in temperature. If it's just temperature, it must be in Kelvin. So plus 273. And that's going to give me a final temperature of 298 Kelvin. So now I have all of the building blocks I need. Let's go on ahead and solve this problem. So that is going to be delta G equals delta H minus T delta S. So delta G equals delta H, which is right here, negative 198. And we know it's in kilojoules minus T delta S. Okay, and that is going to be T, which is 298 times delta S in kilojoules, negative 0.187. And that is going to finally equal out to negative 142.27 kilojoules. And there you have it. So to sum up, I wrote the reaction in a reverse form, in a final minus initial form, so I can just look at that and fill the numbers in. And then I used the chart for both delta H and delta S and filled those into the same reaction. Came up with my answers. Watch carefully my units. One is in joules, one is in kilojoules. Delta G should be measured in kilojoules. So I went ahead and converted my joules to kilojoules, a very important step that's often missed, and then plug those into this reaction and you are done. Okay, for the naming acids and bases, I'm actually going to step away from this worksheet because the naming acids and bases turned out to be a big problem for a lot of students. So let's take a deeper dive into naming. And so for that, let's move on to another sheet that I uploaded. And this should be in your Schoology as well. So follow along with me on this one because again, we had a lot of missed points over this, and this should be relatively easy. So let's start off with a bit of a notes here. And we have rules for naming acids. Now, bases are pretty easy. Bases end in hydroxide, so it's just the name of the cation plus hydroxide. So cool. The only time it can get any difficult is variable charge, but we'll mention that. For acids, on the other hand, you do have some rules, and this is for if it's ide, if your anion ends in ide. Now remember, ide just means monoatomic. So in this case, we know these are all +1, +2, We know these are -1, -2, -3, and so on. And so if I put together, say, sodium, our little buddy right here, we see this a lot, sodium and chlorine, that is called sodium chloride. And since they're 1 to 1, they would just go together, NaCl. Now, what does that have to do with acids? Not a lot, other than to bring up ide is what your anion is called if it's a monatomic, if it's just two different atoms put together. Now, that's not to say there's only two of those as two atom types, because if I do the same thing, if I want magnesium and chlorine, whoops, magnesium is a +2 and chlorine is a -1. So swap, drop, and reduce. That's going to be MgCl2 because MgCl is not a thing. But either way, it's still called magnesium chloride or sodium chloride or whatever. Now, getting back to this. So ide, this means this is something that's on the periodic table, two different things. So for an acid, it's going to start with hydrogen, but your anion is going to be from the table. Now, if that happens, think hydro for mono, ic acid. Okay. Now, if it's not a single atom that's on the periodic table going with hydrogen, then what we need to do is we need to start looking at the periodic table. Now, there are a lot of polyatomic ions, but we're just focused on these, and that's going to be a polyatomic ion that ends in 8. So chromate, sulfate, carbonate, whatever. And when you ate, you got sick. So it's pretty much the same as the one above. We just dropped the hydro. So if you see hydro, look to the periodic table. If you don't see hydro, this is a polyatomic ion, and it's a polyatomic ion that ended in 8. So again, acid. And then you have OUS, okay, and that comes from ite. So sulfite, chromite, whatever. So ite turns into OUS. So these are the rules, and you definitely need to know these. So let's go ahead and take a look at some of these here. So HF, that's hydrogen, and that's fluorine. Those are monoatomics. And so I'm going to plug that into here, hydroic acid. And for fluorine, so we're going to do hydro, and then we're going to change, if it was just your old-fashioned ionic compound name, we would call that hydrogen fluoride, but that's not what we're calling this because it's an acid. So the ide turns into ic, and that is hydrofluoric. And I may spell some of these wrong, but we'll live. F And if you accidentally spell one wrong, I'll survive as long as I know that you were using fluorine and you were changing the N to ic, we're fine. So hydrofluoric acid, probably something you've heard of. Okay, here we have barium and we have hydroxide. So this is a base and it's just simply called barium hydroxide. Cool. Okay, we have potassium and hydroxide. So again, another base. And here we have H2S. So, okay, again, monoatomic. Now, S stands for sulfur, and sulfur has a -2 charge, which is why we had to have two hydrogens to make that work. So we are going to go with the hydro, since this is a monoatomic, okay? I guess you call it binary acid, so two different atoms. So hydro, and then sulfur, we're going to turn that into sulfuric, SUL. Uh, okay, so not hydrogen sulfide, I turns into ick, so hydrosulfuric acid. Back. Okay, H2SO3. Okay, starts with a hydrogen. It's an acid. There's three different atoms in here, so there must be a polyatomic at play here. So what is SO3? Well, let's find out. Okay. So I've got a SO4 and I have an SO3. Now I want to make sure I use the right one. And SO3 is sulfite, ITE, sulfite. Okay. And so H2SO3. So if I have an ite, that's going to turn into OUS. All right. So sulfite turns into sulfurous. So let's write that. So we're going to start with that. UROUS. No hydro. Hydro is for mono. Hydro is for binary acids. That's not one of these. This has a polyatomic, so we're just going to call it sulfurous acid. Aluminum and hydroxide. See if you can guess what that's called. Aluminum hydroxide. Okay. Hey, calcium hydroxide. Let's just move on. That's called calcium hydroxide. You know this. Okay, so H3 with PO4. Well, PO4, that's what is PO4? Let's find out. Here we go. It's phosphate is where my PO4. Now, this is a -3 charge, which means that if I was simply trying to go from the name to the acid, then what I would do is say, okay, this is a -3. Hydrogen is a +1. So I would predict that I would need 3 hydrogens. So it would be H3PO4, and 8 turns in ick. So let's go ahead and take a look. Did they do H3PO4? I'll bet they did. So H3PO4. And so the name for that one, remember 8 turns into ick. So phosphate is going to turn into phosphuric. Let's see. Hey, so 8 and got it. So phosphate to phosphoric. Again, if you have some slight misspellings on these, it's fine. It's fine. You know, as long as I can tell what you're talking about. Okay, so NO3. If I go back and look at that, NO3, what's NO3? Help me, this isn't binary. So NO2, okay, that's nitrite, but I don't want NO2, I want NO3, which is nitrate. And I ate and I got sick. So NO3 turns into nitric. Now let's just say, for the sake of discussion, what if it was NO2? What if it was nitrite? Well, then it would turn into OUS and this would be nitrous acid. But it's not, it's nitric. Okay, and then lithium. I forgot the R in there. Lithium hydroxide. Okay, let's move to a couple of names to formulas, equally important, if not perhaps more so. So acetic acid, I see no hydro. So this is not a binary acid. This is using a polyatomic ion and it ends in ick. And so ick started with 8. So I need to find something that kind of starts with ace and ends with an 8. So let's see, what do we got? They're in alphabetical order, so let's move up here. And here we go. Something that starts with ace, 8. This one makes sense. Now, to make this an acid, I'm going to need to add a hydrogen to this. Okay, and a lot of people, and it totally makes sense why they would have done this. A lot of people wrote this as C2H4O2 with no charge. I get why people wanted to do that, but for this, what we want to do is we want to keep our cation and our anion separate, so that if this were to break up in, say, a double replacement reaction, or in this case a neutralization reaction, we would be able to recombine this cation and anion. So it's better to keep them as a cation and anion. Your polyatomic ion sheet may have something like this. I think it's CH3COO or something like that. If yours has that, just kind of ignore it. That's for organic chemistry. If you're interested in that, let me know. I'll show you how to draw it. But for this, let's stick with the CHO232 and put that together. And this is going to be a 1-to-1 because we have a +1 and a -1. So this is going to be H, and that's going to be our acetic acid. Okay, fluorous acid. Again, no hydro, so I'm not looking for a binary acid. I'm looking for something that ends in O. So I have OUS, and OUS came from ite. So I'm looking for something that starts with chlor and ends with ite, which I just said the name of it by saying that, and that is chlorite, which is right there, chlorite, which is ClO with a -2 charge. Whoops, and whatever. So that's ClO -2. Wait, that's not right. I don't think so. No, ClO2 with a -1 charge. My mistake. Okay. Since that's a -1, we're going to put a single hydrogen with that, swap drop, HClO2, and we're done. Hydrobromic acid. Hey, hydro, this is going to be binary acid. This is going to be from my periodic table. So bromic, what was bromic? Well, let's see. Where's my bro? Where is my bro? Okay, we know it's going to be negative because it's an acid, a binary acid. So we're going to stick in the negative carriers. And here we go, bromine. That's my bro. And that has a charge of -1. So with hydrogen, that's going to be a 1-to-1 pairing. And so this is just going to be HBr, nice and simple. And then let's see, chromic acid. I feel like we've already seen that, but no, I guess not. Okay, so ick, and ick comes from 8, and it starts with crow. So what did the crow eat? What's my crow ate? Okay. Oh, here we go. Here's an 8. Here's a crow. And that's CrO4 with a -2 charge. And so therefore, I'm going to need 2 hydrogens to balance this one out. So let's go ahead and write that down in our sheet here. Okay, and the chromic acid. So again, I've got 1 hydrogen. I've got chromate, which is CrO4 -2. So I'm going to need 2 hydrogens. H2, CrO4. Charges are gone because I balanced them by using 2 hydrogens. So great. Okay. And last 2, let's go ahead and work these out here. Gallium hydroxide. Oh, hydroxide. This is going to be a polyatomic. So I know I'm going to use hydroxide, which is OH-. Let's take a look at old gallium right here on our periodic table. Oops. Where is our gallium? Let's see. Oh, this is going to be a positive. And oh, there he is. There's gallium. And what's the charge of gallium? Well, it's in the same row as aluminum, which we know to be +2. Skip the transition. This is a +3. And for reference, carbon can be either a plus or -4. but that kind of comes up more during oxidation numbers and stuff. So we know this is a +3 for gallium, and we are going to match that with hydroxide, which is a -1. So gallium +3, swap, drop, and reduce, and that is going to be gallium with 3 hydroxides. And I use the parentheses so that I don't accidentally make it look like I have only 3 hydrogens and not 3 hydroxides, which is what I do have. Iron 3 hydroxide. So remember, if I tell you a 3, if I give you a Roman numeral, that is because it is here. It is one of your transition metals, or, like lead. There's a few other ones in there. Tin. You have variable charges for these. And so if I say 3, I'm not telling you to use 3 irons. I'm telling you that the charge of the iron is, in fact, a 3. So, and then hydroxide, well, we already know that, old friend. And so again, this is a +3 with a -1. So again, I'm going to write this as FeOH, and I need 3 of these bad boys. If this was iron 2, it would just be an iron with a +2 charge, which would mean I'd need 2 hydroxide, not 3. If it was iron 1, if there was such a thing, then it would be a 1-to-1 match. So if you see this here, this is just kindly telling you what the charge is, because in most cases, you already know what the charge is, but in some cases you don't. Okay, that finishes up this. Let's go back to our review. So let's just skip that because those were already in there anyway. And for here, I'm going to pop up a calculator, and I'm going to show you myself doing this math so that you can see what I'm doing. Okay, so here I'm going from concentration to concentration. And so what I want to do is, let's pull this up here, is I want to keep in mind that concentration of H plus times the concentration of OH minus is equal to 1 times 10 to the -14. That's how many self-ionization of water. That's, water will kind of break into its ions in a very small amount, exactly 1 times 10 to the -14. And if we have a bunch of extra H plus versus OH minus, that's how we can tell if something's an acid or a base. So that's kind of the whole basis of this thing. Okay, and I have hydroxide and I want H plus. So what I'm going to do is isolate H plus by dividing both sides by the hydroxide, or the concentration thereof. And the concentration is right here. It is 5.42 times 10 to the -5. Okay. Okay, so I am going to put this into my calculator. And if you watch here, I'm going to use a parentheses 1 second log, which brings up the times 10 to the, so times 10 to the -14. And I'm going to double close my parentheses and then divide that by 5 times, 5.42 times 10 to the -5. Again, double closing my parentheses. That way I can keep it all together, hit enter, and I've got 1.845. And look all the way to the right, you'll see times 10 to the -10. So let's just call this 1.85 times 10 to the -10. Okay. So next, I have the concentration of hydroxide, and I'm sorry, I have a concentration of H plus or hydronium, and I want the concentration of hydroxide. And so what I'm going to do is basically the same thing here. I'm going to do 1 times 10 to the negative 14 divided by the concentration I do know, which is 1.2 times 10 to the negative 3. Okay, and so in my calculator, I'm going to do 1 times 10 negative, I'm sorry, second log, negative 14 divided by 1.2 second log. This brings up my 10 to the and negative 3. Double close my parentheses again and hit enter. And I get 8.3333 times 10 to the negative 12. So 3 times 10 to the negative 12. Okay, so while we're here, let's take a look at ways I can go between, say, pH to POH, stuff like that. So the question is not on here, but let's just say we wanted to go from a concentration, which we do, and that can be H plus or OH minus, to a pH or POH, which is going to be a 0 to 14 number, where concentration is going to be a 10 to the negative number. So 0 to 14. So let's just go ahead and take the concentration of hydroxide, which we just solved, and take that to the POH. Then what I'm going to do is in my calculator, I'm going to type negative log of the concentration. So I'm going to type that in as 8.33 times 10 to the negative 12. And in my calculator, I am going to get an answer of, let's see, 11.08. And that is going to be my POH since I use the concentration of OH. So 11.08. Now we take 11.08 as our POH, and what I want to do is just go right back to do a concentration. And what we're going to do there is basically called the anti-log. So I'm just going to hit second log, no parentheses, to the negative pH or POH, in this case 11.8. So second log, negative 11.08, and see that we get 8.317, etc., times 10 to the negative 12. So not exactly the same number, but we did do some rounding, and it's pretty close, times 10 to the negative 12. So there I went from pH or POH back to concentration. Okay. So that's how you go back and forth between those. And keep in mind, well, we'll take a look at that one down there. Okay, what is the pH of a solution with a hydroxide concentration of 6.217 times 10 to the negative 10? So I want to go first from concentration of hydroxide, and I want to take that to the POH. So I am going to go ahead and put in negative log, so negative log of the concentration of 6.217 times 10 to the negative 10, close my parentheses, and that is going to give me an answer of 9.206. Okay, now this is going to be my POH. Now, pH plus POH equals 14. So therefore, 14 minus my POH of 9.206, or second answer if you want to use that because it's convenient, is 4.793, etc. So 4.79. And now I am the proud owner of a pH, which is what the question wanted. So there is my answer. So pH to pOH is pretty easy. 1 plus the other is equal to 14. Again, going from concentration to concentration is just 1 times 10 to the negative 14 divided by the concentration you do have. To go from concentration to pH or pOH, what you're going to do is use the negative log function and negative log of the concentration. And to go from a concentration to a pH or pOH, that concentration of OH minus is going to equal a pOH, and a concentration of H plus is going to equal a pH. To do that, you're going to hit the function second log just to bring up the 10 to the same thing we use for scientific notation times, and then with the exponent being the negative pH or pOH. Okay, so the last thing we're going to do is called titrations. So let's go ahead and jump right into this. First thing I'm going to notice is I am given a volume and I'm given a molarity. So these questions really just come down to the fact that molarity or concentration equals moles over liter. Okay. And so if you have two, you can solve for the third one. So real quick, let me just kind of show you how I do that. So if molarity equals moles over liter, you can either put m over 1 and cross multiply. That way works. What I do is kind of visualize these in a triangle. And molarity is to the left, moles are on top and liters on bottom, and I can just cover up whatever it is I want to solve for. So you can't really see this on the screen, but let's just say I covered up moles, and what I'm left with is m times L. If I cover up liters, then I'm left with moles divided by molarity to solve for liters, and so forth. So as long as you have two, you can solve for the third. Okay, and so I have hydrofluoric acid and I have magnesium hydroxide. And what I want is the concentration of my magnesium hydroxide. But the problem is I can't do that if all I have is the volume. I also need the number of moles because concentration is moles per liter. But I can figure out how many moles it took to neutralize this. So let's figure out with the hydrofluoric acid. So the first thing I need to do is I can see this does not go together 1 to 1. So I'm going to need to balance this equation. So I'm going to do HF plus MgOH2 reacts to form. Now I'm going to break these apart. So H plus and F minus, and I'm going to break this apart, and magnesium is always a +2, and hydroxide is a -1. So the way this works is they just swap ionic partners. So I like to do water first because a strong acid and a strong base neutralization will always form a water and a salt. So I'm going to take this H plus, and instead of being with the F minus, it's going to choose the OH minus. And so I'm going to write water in my kind of special way when I'm doing these as HOH. This keeps the hydroxide separate, and that makes this a little bit easier. Plus, now I have magnesium and fluorine, and magnesium is positive, so that's going to go first. And with a +2 charge, I'm going to need 2 fluorines in order to make this work. So MgF2. So MgF is not a thing. And if you don't do your swap drop, you're not going to be able to balance this. So let's go ahead and erase these notes, kind of make some room here. Now I need to go ahead and balance this. So to do that, hydrogen that's not part of hydroxide, I've got one here and one here, so that's cool. Fluorine, I have got one here and I have two here. That's not going to work, so I'm going to put a two there. That did throw off my hydrogen, but I'm not worried about that until I get to the end. So magnesium, I've got one here and one here, so those are good. And hydroxide, I've got two here and I have only one here, so I'm going to put a two there. And that also solves my imbalance with the hydrogen. So this is why I usually like to wait until the end, because a lot of times it'll take care of itself. Okay, so 2 moles of hydrofluoric acid are going to react with 1 mole of magnesium hydroxide, which is very important for me to know this. So let's figure out, well, how many moles of hydrofluoric do I have? Well, I know that 0.28, which is my concentration, is moles over liters, and I know 0.025 liters. So therefore, X equals, and I'm going to put that in the calculator as 0.28 times 0.025, and that's going to equal 0.007 mole of hydrofluoric. So this is good. I needed to know this. Now, this is not a 1-to-1 ratio. If it was a 1-to-1 ratio, that would mean I also have 0.007 moles of magnesium hydroxide. But since this isn't, I need to figure this out. So 0.007 moles of hydrofluoric, and let's convert that to our base. And so mole of HF, I'm bringing my unit down, mole of MgOH2, and according to my balanced equation, that is going to be a 2-to-1 ratio. So I'm going to go ahead and fill that in. So 2-to-1, and that is going to cancel out moles of HF and leave me with moles of magnesium hydroxide, which is which is awesome. That's what I want. So this means that I have 0.007 divided by 2, which is going to equal 0.0035. So 0.0035 moles of MgOH2. So now I'm almost there. I have moles and I have liters right up here. So cool. So molarity is moles over liter. So molarity equals 0.0035 moles over my liters, which is right here in the question. So 0.047 liters. So divide, and my answer is going to come up to 0.0745 molar. So this is my concentration of the base MgOH2. So to refresh, or just a review, sorry, what I did was I figured out first my balanced equation. So this way I know what the mole-to-mole ratio is between the acid and the base. I know it's not 1-to-1 because I've got a 2 here. So this did not go together 1-to-1. Now, just because, with acid and base, hydrogen is always a +1, hydroxide is always a -1. And so I know if this went together 1-to-1, that my cation must, and anion that was with it must have also been a +1 or -1. It balanced out. Okay, so next what I did was I took my concentration in my liters and solved for moles of hydrofluoric acid. And from here, I did my mole to mole ratio. So however many moles I have of my acid, I can use my mole to mole ratio that's in the formula to find the number of moles of the hydroxide. Once you find that, you're in pretty good shape because you also have liters right here for you. Oops. And just do moles divided by liters. and that is going to give you your molarity. Now, this next one, you can use a shortcut here. Now, you can do exactly what I just did, and you'll be fine. You'll still answer the question correctly. It may take a little bit longer, but it's always going to work out for you. But in this case, I know that KOH is the result of K plus and OH minus, and HBr is the result of H plus and Br minus. So if I break these apart and I put them back together, it's going to balance all out to 1-to-1 because they went together 1-to-1. So I don't really need to worry about this part here. I don't need to do this whole mole to mole ratio thing because I know the mole to mole ratio, it's 1. So when you have this situation, and only when you have this situation, you can use M1 V1 equals M2 V2. Now, again, I'm wanting to say solve for the same thing, concentration of my hydroxide. So this is what I want to solve for. And so to do that, I'm going to divide both sides by V2, which will cancel on this side, and then V2. So therefore, M2 equals M1V1 divided by V2. And then this is just kind of a plug and chug. So I'm going to put my M1, which is right here, and my V1, which is right there, and my V2, which is right here. I'm going to plug these into this formula. And so I'm going to put 0.195 as my M1 times 0.037 divided by my V2, which is 0.0536 liters. And then when I put that in the calculator, I'm going to get 0.135 equals my M2, or the concentration of KOH. So this is a shortcut. It only works with the 1-to-1 ratio. So be very careful that you don't try and use this when it's not a 1-to-1 ratio. Okay. All right. I think that pretty much sums it up. So, make sure you go over all this and you're comfortable. If you have any questions, feel free to ask me or your teacher, and we will see you next time.